Hi there, and welcome to Raelene Math. Let's take a look at three functions we've seen before: sine x over x, cosine x minus 1 over x, and e to the x minus 1 over x. But this time, instead of looking at x equal to 0, which was a discontinuity of these three functions, and specifically each function had a hole when x was equal to 0, let's look at a different behavior or different part of the graph. Let's look at the end behavior. Now the end behavior is specifically as x approaches positive infinity, or as x approaches negative infinity on the graph. We're interested in knowing what the behavior is of the function. What height does y approach? Does y approach a finite height and therefore have a horizontal asymptote, or does y approach infinite heights? So we'll take a look at the first function. Sine x over x we recognize as this function with a hole of the graph at 0, 1. But we're not interested in zooming in at x equal to 0. We're interested in zooming out, specifically on the right side as x approaches positive infinity, or on the left side as x approaches negative infinity. One of the first things we can consider then is that the sine x is a bounded function, and we know that the height of sine x is bounded between two horizontal lines, y equals -1 and y equals +1. And it turns out that we can divide each of these terms by x. This is really because of the even symmetry of this trig function or this sine x over x function that this works. And we can see that the blue sine x over x function is always bounded between these two reciprocal functions. Let's take a look in another view. Here's sine x bounded between the two horizontal lines, and therefore sine x over x is bounded between -1 over x and 1 over x. We can see that, let's look at a different window to see it a bit better. No matter what x-coordinate we're dealing with, the blue graph is always bounded in height between the red and the green, and same on the other side. And so what we have is that the sine x over x graph is bounded, and since the red and the green graphs on the right side tend to the same height, namely they tend to a height of 0, so must the blue graph, and the same thing on the left-hand side. So what we would do is consider using the notation of limits here, and whatever height the green graph approaches and whatever height the red graph approaches as x approaches infinity must be bounds for the height that the blue graph approaches. From our knowledge of the reciprocal function and its vertical reflection, the -1 over x graph approaches a height of 0 as x approaches infinity when we zoom out on the right-hand side. Similarly, the red graph also approaches a height of 0, and the height that the blue graph approaches must be bounded in between these values. And so we say that the limit as x approaches infinity of sine x over x is between or equal to 0 and 0. Because these two bounding values, the bottom height and the top height, are the same, we can conclude that the limit as x approaches infinity on the sine x graph over x, sine x over x, must also be equal to 0. This result is known as the Squeeze Theorem or the Sandwich Theorem. Now, if the two end boundary values of the 0 and the 0, if they were different, then we couldn't apply the Squeeze or the Sandwich Theorem to make any conclusion. And either the limit doesn't exist or we'd have to use some other technique to find out why. This result is also true on the left-hand side, and so we have that the left-hand end behavior and the right-hand end behavior are the same. And what that means is we have a horizontal asymptote at y equal to 0 on this function. Looking at the graph of this function, then, we can start to see that the zoomed out behavior is the horizontal asymptote. If we zoom out far enough, we can't really see a lot of things going on. So I'm going to turn off the green and the red graphs as well as the x-axis. And when we do that, we start to see that the horizontal or the blue graph looks more like a horizontal line when we zoom out. There is still some non-constant behavior going on at the origin or at other points on the graph, but we are focusing our attention on the end behavior, the right-hand behavior and the left-hand behavior. What does y do when we zoom out far enough? Well, this graph indeed looks like the line y equal to 0. And if I turn off the blue, if I hit the graph and I turn off the blue, we'll see the purple one underneath. And if we turn the blue on and the purple off, we see the blue. And so we see that we have a horizontal asymptote of y equal to 0 for this function. Now let's take a look at the cosine x minus 1 over x function. This function has odd symmetry, and so whatever we consider happening on the right side, we can rotate 180 degrees and get the remainder of the graph in the other side of the y-axis. So we can consider taking a look at cosine x bounded between two horizontal lines again, y equals -1 and y equals +1, and we can subtract 1 from all sides of an inequality and maintain the inequality. So I can get cosine x minus 1 by subtracting 1 from -1 and subtracting 1 from 1. Now if I want to get cosine x over minus 1 over x, I think it's no problem really to divide here by x, but in fact something I didn't tell you about in the last example was that it is a problem when dividing through by a variable in an inequality, because a variable is able to vary, can be positive or negative, and we are familiar with inequalities. If we multiply or divide through by a negative, we have to flip the inequality sign. So I'm going to focus restricting my attention on x greater than 0 so that I'm only dividing by a positive number. And then by the odd symmetry of the f of x function, whatever graph I get on the right-hand side of the y-axis, I'm just going to rotate 180 degrees to get the remainder of the odd graph. So I'm going to see that my cosine x minus 1 over x graph is bounded by -2 over x, which is this red graph down here, and by 0 over x, which is actually just 0, y equal to 0. And so in this region, my blue graph will be bounded. Now, as x approaches infinity, the purple graph already is 0, so it approaches a height of 0. The y-coordinate approaches a height of 0. And the red graph, which is now this -2 over x function, also approaches a height of 0 as x approaches infinity. And so we see that by the same sandwich theorem for the right side, as x approaches infinity, the height of the cosine x minus 1 all over x function also approaches a height of 0, and therefore the limit is equal to 0. Well, we can do the same kind of investigation and boundedness on the other side, and we can see that x approaches negative infinity also means that y approaches infinity. Rather, y approaches 0. So we have a horizontal asymptote at y equal to 0 on both the left and on the right sides of this function. The last graph is a little bit different, and here I've drawn the graph of e to the x minus 1 over x, which also had a hole at 0, 1. But when we look here, we've got two different graphs. We've still got the blue graph, e to the x minus 1 over x, and I've shown the graph of y equals e to the x as a comparison. We don't have the same zoomed out shape on the left side as we do on the right side. For both the purple graph and the blue graph, as x approaches negative infinity, the y-coordinate approaches a height of 0, so we have a left horizontal asymptote of or at y equal to 0. But there is no boundedness on the right-hand side. The y-coordinates do not stop or become lower than or between a set of finite heights on the right-hand side. So for the right-hand side, both the purple graph and the blue graph have the same behavior. As x approaches infinity, y approaches a height of positive infinity. And so we would say that the left-hand height exists, or the left-hand limit, as x approaches negative infinity on the graph of e to the x minus 1 all over x, y approaches a height of 0. But the right-hand limit, I'll just write it as the right-hand limit or the right-hand end behavior. We don't have an asymptote because y does not approach a constant value, and therefore the limit as x approaches infinity on the same graph of e to the x minus 1 all over x equals infinity, and that's not a finite value, so the limit does not exist. So just going back to take a look at our summary, we have some information here about all of the graphs. You can take a screen snapshot, and you can add that summary to the summaries from other videos. If you like what you see, click like and leave a comment down below, and don't forget to subscribe. Thanks for checking out Raelene Math.